So we've taken a little break from looking at different kinds of counting techniques to look at a specific example, the patterning idea of Pascal's triangle and the binomial theorem. For this lesson, we're going to go back to our basic counting, and we're going to try and combine it with some probability. So again, not something new, but we're going to use something we know how to do in a slightly different way. So our whole idea of probability is find the ways your event can happen and divide it by all the events that could possibly happen. So let's start with we're just doing examples today, okay? Let's start with our typical example. We have a committee. A committee of 3 people is to be selected from 10 males and 8 females. That's a combination question. We know that because we're making groups of things. But I'm turning this into a probability question by asking, what's the probability there are exactly 2 males on the committee? So, how many different ways could I pick any committee? Well, the committee is 3 people, and we have a total of 18 people. So the total possible committees we could make are 18 choose 3. But the specific that we need to have is there has to be exactly 2 males. Well, to pick the males, there's 10 of them, and I need to choose 2. But it implies if there's 2 males in the committee that we have a female in the committee. Because remember, we have a committee of 3. So we need to multiply that with our females, 8 of them, choose 1. A hint for you when talking about probability, these 2 numbers added together always makes that number. And these 2 numbers added together should always make that number. Okay. Just to figure this out, you can do it in 2 separate ways. You can put it all in your calculator at once, or if you want to, do it as fractions. So the top number is 360, the bottom is 816, or the decimal version 441. I'm okay as fractions. If you leave them that way, totally fine. If you want to turn to a decimal, also fine with me. Let's look at part B. What's the probability the committee is all women? So, events, all women. Well, all women, that's what I need to have. I have 8 women, so I need to have 3 of them, which implies no men, so 10 choose 0. Out of, how many ways can I make committees? 18, choose 3. And there we go, 56 out of 816, or decimal version 0.0686. And let's try part C. The probability there's at least 1 man on a committee. Oh, at least 1. Well, that implies cases. I could have 1 man, or 2 men, or 3 men. Now, we've talked about faster ways of doing this kind of question, the idea of the indirect method. If I want at least 1 man, well, the complement to that is no men. That's the opposite of at least 1. So if I want to know my no men, sorry, I'm just going to change the order of this, okay? If I take my total and I get rid of the case of no men, I'll be left with at least 1. But we're not counting necessarily here, we're looking at probabilities. So if we think of this in a probability manner, the total is always 1. No men implies all women. Hey, I've figured that out already. That's this number. So if I wanted the probability of having at least 1 man, I can get rid of my cases I don't want. I'll be left with what I do want. There's a 93% chance of having at least 1 man on this committee. Okay, so we're still using that idea of indirect, but here we're thinking about probability manners. So when we talk about total, we talk about total in terms of 1. Or if you did as a fraction, totally fine. You could do it as a fraction where all the different possibilities, well, it's still 1, but minus 56 over 816, which gives us 760 out of 816. That works too. Okay, so fractions or percents or decimals. I'll try some more examples. To win a grand prize in a lottery, you need to match 7 numbers chosen from 1 to 27, and order doesn't matter. So what you pick, who cares what order you pick them in, what matters what's on your card. I want to win the grand prize. What's the likelihood of winning that? Well, how many different ways are there of picking my numbers? 27 numbers to choose from, and I pick 7 of them. What's the likelihood I get all the right numbers? Well, the right numbers, there's only 7 of them, and I need all 7. So in other words, 7 choose 7. Or, if you will, there's one right way out of all the different possible combinations. 888,030 combinations. Not very likely you're going to win. Part B. Second prize, you have to match 6 winning numbers. So we can do the same idea here. But instead of having all the right numbers, I only need to get 6 of them. So if you think of this as 7 winning numbers and I need 6 of them, it implies that I have one of my numbers that's not a winning number. If there are 7 winning numbers, how many non-winning numbers are there? Well, there's 27 altogether, so there's 20 non-winning numbers. And somehow on my card, on my selection, I picked one of those. So 20, choose 1. Out of 27, choose 7. And I won't go back to A for just a second. Notice that I didn't write in this part of it, the non-winning numbers. I could have, if I wanted to, implied there's 20 non-winning numbers and I chose none of them. But you don't have to show that, because 20 choose 0 is 1. There's only one way of doing it. That doesn't change my answer. But in the second one, I did need it because I needed to pick one of those non-winning numbers. So what do we end up with? 140 out of the 888,030 different possibilities. And we'll try some more. The more of these we do, the easier it gets. We're going to see some themes. So what's the probability of having an all-red 5-card hand in the game with a standard deck? So I need to get all red cards. Well, how many ways can I pick any deck, any 5-card hand? 52 cards. I have 5 of them in my hands. How many ways can I get red cards? Well, there's 13 of each suit. 13 diamonds and 13 hearts makes 26 red cards, and I want 5 of them. Here's my probability is 6, 5, 7, 8, 0 out of, big number here, make sure I get this right, 2, 5, 9, 8, 9, 6, 0. Or if you did yours in decimals, 2, 5, 3. Okay, again, when you're picking a hand from a deck of cards, the order you get the cards in doesn't matter. It just matters the ones that you have in your hand. Okay, so let's take that to the next stage. What's the probability of having all the same suit in a 5-card hand? So I'm hoping you guys can try this one yourselves. And we're still doing 5-card hands, so 52 choose 5, but they have to be the same suit. So it could be all spades, or all clubs, or all hearts, or all diamonds. So if you think about that, hearts, or clubs, or spades, or diamonds, well, that's cases. If I think about the hearts case, how many ways can I get all hearts? There's 13 of them, and I need 5. How about clubs? Well, there's 13 of them, and I need 5. Spades, 13 of them, and I need 5. And same thing for diamonds. So I could write each of these out separately, and the bottom stays the same every time. Okay, that's the same, that's the same, that's the same. And add them all together. Or, if you will, I could do 13 choose 5 for any of my 5 cards times the 4 different choices, hearts or clubs or spades or diamonds, divided by 52 choose 5. Sometimes it's faster to write things out as a multiple rather than writing out each separate case. But if it doesn't make sense in your brain, write out each separate case. That might help you. 5,148 out of, I use my calculator, 270725. That's a simplified version, okay? Or the decimal, 0.019. And less likely to get 5 of the same suit than it is 5 of the same color. Okay, let's try a couple more. A checker. Based on a checkerboard is shown. The checker may move diagonally upward, although it cannot move into a square with an X. The checker may jump over the X into the diagonally opposite square. What is the problem? The checker jumps the X. So this is a path problem. This is the idea of Pascal's triangle. Where can the checker move? Well, it starts where it is. And it can move here one way, and goes directly there, or here, or here, here, here. Pascal's triangle. Same thing in the other direction. It could also move to this spot. It can get there from this one or this one. So in other words, there's two ways of getting here. 3 here, 4 here, 5 here, 6 here. This 6 is this 6. It's the only way we can get there. And we got 3, because I could only go this way. Got 6, I got 9, I got 10. This one could go 9, 19, and 28 either direction. And we got to deal with the X. Now I can't go through the X, but I can jump over it. So this 5 could go right to here, or these 19. So there's 24 different ways. And same thing with the 10. The 10 could go over, along with the 6, and make 16 different ways. So, what is the probability that the checker actually jumps over the X? How many paths jump over the X? Well, these are all ones that went over the X, right? Sorry, I put that circle in the wrong spot. These are all ones that jump over the X, right? These 10 go this way over the X. These 5 go this way over the X. So we end up with 15 different paths that go over the X. How many paths to the top do we have altogether? Well, if I add up these, I end up with 74 different paths to the top. So what's the likelihood I jumped over the checker? 15 out of 74. All right, that takes us to the end of the unit. More counting methods. So our test coming up in 2 days. We'll cover all the different counting techniques, combinations, repeated items, Pascal's triangle, binomial theorem. We're going to practice them tomorrow with a review, but try these ones first.